So thank you very much for giving me the opportunity to talk about one of my favorite topics, which is portable X-ray fluorescence. And the method has been around in archaeometry for quite a while. So it's fair to ask why we need to discuss standardizing it now, and if it's really nothing more but window dressing. The devices themselves are well characterized by being portable. So especially by their size, they're about the size of a hairdryer, which is nice to have it on the plane. So that works very properly. You can use them directly in the field, in the museums, but of course also in the traditional laboratory settings. The questions normally posed to the method are those of presence and absence of chemical elements, for example, arsenic if we talk bronze, or phosphorus if you want to identify activity areas. Of course, also those things like where was something made, so origins, and how was it made, so recipes. Objects we can analyze are of different materials, so they were created for analyzing metals, modern metals, but we apply them to archaeological metals, to stones, pigments, pottery, soils, also bones, but there's the issue that we can't measure elements lighter than magnesium, so there we could only get the heavy elements like metals. The benefits of the methods are that it is, well, portable. It is quite quick, so we can do a sample in between 2 and 20 minutes, depending on material and measurement time, so it's also quite cost effective. It can be done semi to non-destructive, we get instant results, and this also allows collaboration directly in the field. The devices are equipped with their own X-ray tube, so they have a heated element which emits electrons. Those hit a target and get slowed down pretty abruptly there, thereby releasing a certain kind of energy, which is called X-rays. Those X-rays hit the sample in front of the device and knock out electrons from the inner shells. Then an electron from an outer shell falls in and thereby releases a certain kind of energy, which is called X-ray fluorescence or characteristic X-rays. The amount of energy is directly related to the atom size, so this is why lighter elements are more difficult to analyze with the devices. Also, if we have a look at the samples themselves, those very tiny energies get pretty easily absorbed in the samples. Also, as we're working with light, light gets reflected on the surface, so sometimes we get very weird results if the surface isn't smooth. Another thing is how the sample is constructed. So we can measure powders, and they have a completely different particle size, a completely different matrix than if we work with ancient pottery, which is my focus area. Still, regardless which material we're working with, we need to know that the method is valid. To define validity of a method, we use especially the terms of precision and accuracy. Precision thereby describes the scatter of values around a mean, and accuracy tells us if the value we're getting is really the one we wanted to get. Now, in literature using portable X-ray, we find the nice phrasing, my device is working precisely, which is great, but they don't say what that means. So there would be standard deviation or variation coefficient where we could set benchmarks to define what working precisely means, but it didn't happen up to now. Same thing with accuracy. We can test for accuracy if we compare PXRF values with laboratory analysis of the same samples using linear regression. And there are criteria to define how well that linear regression is explaining the relation of those two sample sets. But, well, there are no benchmarks for that. Also, things are happening with the device we don't quite understand. So there are measurements of the same sample done in different places through 2023, and we can see the values do differ. We don't know why, and we don't even know if it is important. Another thing we have is related to samples themselves. We know that light elements can only be detected very close to the fluorescence, but we don't know what the algorithm does if the object gets farther away than it should be to really detect the elements, because the algorithm will always give us a result. Same thing in regard to moisture content. For example, we know that wet samples are difficult because the water film is shielding the X-rays, but we don't have a benchmark how wet, for example, pottery can be before the results get completely screwed. So what I want to do in the next 3 years is studying some of those topics further. So I will first create a baseline. So I have a lot of pottery now that I document, that I measure with several PXRF devices to know their chemistry. Then I will divide those pottery samples into subsamples and put them through different experiments. One of them will be, for example, on moisture content. So I will completely waterlog the pottery and then dry them slowly and measure them in different steps of drying to see when the values are getting fine again or how long they are completely off. Another thing I want to test for is how do the devices behave? Because I have seen that maybe environmental conditions have an influence on the precision and the accuracy and the overall performance on the devices. So I want to put them in a weathering chamber and test for temperature, humidity, air pressure, whatever has an effect on the devices themselves. Also, I would like to address that annoying thing about precision and accuracy in PXRF. I want to set benchmarks because I think we need them to really know how well the devices are working, but also to have the opportunity to compare devices and methods. So summing up, for me, I think we are on a very, very good place, or in a very good place in the moment with PXRF, because we know a lot, but still we kind of don't know anything. So discussing standardizing now is quite a good idea. So I think it is everything but window dressing in the moment.